Greetings everyone, I'm Stevan Rakocevic from University of Montenegro, and here I am to present our paper titled Multi-Objective Optimal Allocation of Photovoltaic-Based Distributed Generators in Radial Distribution System. As we know, the high electricity consumption coupled with greenhouse gases emissions has posed many challenges on operation of distribution networks. One promising solution is to integrate distributed energy resources, which will be located near consumer areas, which can lower power loss and make energy transfers to end users more efficient. And if they are renewable based, they leave negative impact on environment. In order to fully utilize the potential of these resources, we need to find the optimal location for their connection on the existing distribution network. And this is the topic which is very popular in the research, and authors in different papers present different algorithms for solving this problem. The most popular are meta-heuristic algorithms, but what we find is their drawback. Optimal solution highly depends on initial conditions, and it can vary during the different runs of the same algorithm. Some authors, like we do, propose mixed integer nonlinear programming, but they are not specifying the exact algorithm or the method which is used for finding optimal solution. And lastly, there is mixed integer linear programming, but it requires the linearization of the optimal power flow and does not solve the nonlinear part of the problem directly. In this paper, we addressed the multi-objective allocation of photovoltaic systems. We know that those systems convert energy from the sun or solar energy to the direct current electrical energy. Their main characteristics can be presented using the voltage current and the voltage power relationships, with focal point being the maximum power point, where a PV array is producing the maximum power for the given conditions. There are many models for output power in the literature. We chose the model which states that power equals to rated power times irradiance, a fraction of irradiance and rated irradiance when the irradiance is below rated value, and the array is outputting the rated power when the irradiance is greater or equal to the nominal value. In order to make a mathematical formulation of the problem, first we define the equations for optimal power flow. As we said, we are addressing the multi-objective allocation with the goal of reducing power losses and improving voltage profile. So we define two objective functions. One is power loss, and second is voltage deviation. Next part is equality constraints. We use the balancing equations of active and reactive power, and nonlinear constraints. We chose to put the limitations on voltage values, phase angles, transmitted or produced active and reactive power respectively. As for mixed integer formulation, we introduced the binary variable, which is used for finding the optimal location, and we incorporated it to the model of the output power of the array. And in order to limit the number of arrays which were allocated at the moment, we chose to put the limitation on the sum of these binary variables values in all nodes which is defined. As we mentioned, this problem was modeled in General Algebraic Modeling System, or GAMS, which is a software used for mathematical programming and solving and modeling the variety of the optimization problems. In paper, we discussed some of the main elements of the GAMS environment which were used for forming our model. And you can see the block diagram which depicts how the statements and those elements which were discussed in the papers are grouped together in GAMS code. GAMS has a great feature of containing many different solvers for solving optimization problems. We chose Bondmin solver for addressing the mixed integer nonlinear programming problem we have. Its version, which is embedded in GAMS, offers the 6 different methods for solving mixed integer nonlinear programming problems. We chose the branch and bound algorithm because our problem, due to the optimal power flow, is non-convex problem. Also, In paper, we presented, and you can see on the right side, the steps with these algorithms, branch and bound algorithm takes for finding the optimal solution. As for the simulation results, we consider the PV units which have 500 kilowatts rated power. They have rated temperature of 25 degrees and rated insolation 100 watts per square meter. As for the insolation curve and load changes, we kept it simple. Insolation curve was generated for 21st of June, place with a latitude of 42 degrees, which corresponds to the latitude of Montenegro, using the PV Education online calculator and their solar insolation database. Load changes, we generated them according to the data we acquired about load changes for Montenegro on 21st of June. And also, as a test system, we chose the Radial network or IEEE 33 bus test system. We considered 3 scenarios with 1 PV unit, 2 and 3 PV units allocated. You can see in the table the optimal locations for connecting these devices to our IEEE 33 bus system. Also, you can see the percentage of loss and voltage deviation reduction at peak load demand, which is very crucial. And you can see that those devices contribute to voltage improvement and loss reduction at peak load demand. And this effect increases with a higher number of units which are optimally allocated. Also, there are 2 diagrams depicting the power loss and voltage deviation changes during the 24-hour period. Also, you can see that not only during the peak load demand, which happens around 12 or 1 o'clock, during the production of these optimally allocated PV units, you can see the power loss reduction and voltage deviation reduction. Also, one key point I want to mention is that the purpose of this paper was also to promote GAMS as a valid tool for power optimization problems and also the problems regarding renewable energy and distributed energy resources. Thank you for your time. If you have any questions, I'll be pleased to answer.